perhaps the most fun thing that one can do with the class equation is start to prove the Sylow theorems. So let's just recall what the Sylow theorems are about. So definition, if the order of a group, let's say, is p to the n times m, or p doesn't divide m, so if it has exactly n powers of p inside of it, we say that a subgroup H and G is a p Sylow subgroup if its order is exactly the biggest possible power of p dividing the group. We write Syl p of G for the set of Sylow p subgroups, or p Sylow subgroups, or whatever. Well, the remarkable fact is that they exist. And so let's just see that, and we'll see that using the class equation.
Yeah.
So what does the class equation say? So it says that the order of the group is the order of the center plus the sum of the indices of the centralizers of the various representatives of conjugacy classes of elements in the group. We're going to prove that p Sylow subgroups exist by induction. We'll induct on the order of G. First, I guess we should say, like maybe case 0 or something like that, if p does not divide the order of the group, like if n equals 0 from before, well, then we could say the identity element, the trivial subgroup, is a p Sylow subgroup. And okay, great, we're done. So there are some. Let's ignore that. Okay. Actual, let's say, case number 1 is what if p divides the order of the center of the group? Okay. If p divides the order of the center, I'm going to choose G in the center, order of G is p. So, for example, by Cauchy's theorem, we can do that. And of course, G being central means it generates a normal subgroup. And so I can consider G mod that cyclic normal subgroup. And what do I know? I know that this is a group of smaller order, and so by induction, implies there exists some p Sylow subgroup of that. Of course, the order of that, there exists some p bar inside of G mod G, where the order of p bar is the highest power of p that divides this, which is now, of course, p to the n minus 1. But by the correspondence theorem, such a p corresponds to an actual subgroup p and G, whose order is this times the order of that. And so, boom, p, therefore, is a p Sylow subgroup. Okay, so that's the case where you divide the order of the center, and all we have to do now is where p doesn't divide the order of the center. Okay. If p doesn't divide the order of the center, this is the great case, this is case 2. Well, then p has to not divide one of these indices for some I. Right? If p divides all these and p divides all these, then it would have had to divide that. So if it doesn't, it has to fail to divide one of those indices. But if p doesn't divide this index, I mean, because p divided the order of the group, p therefore has to divide the order of the centralizer. Oh, in fact, not only that, sorry, p to the n has to divide the order of the centralizer, right? So there are no p's, I say it like this, right? The order of the group is the order of the centralizer times the index. P to the n divides that, but there's no p's inside of this, so all those p's are inside of here. So that tells us that p to the n divides the order of the centralizer. But the centralizer is a strictly smaller group, and so by induction, there exists a Sylow subgroup of this, and of course the order of that subgroup is p to the n, but that therefore means that that same subgroup is actually Sylow in the whole group G. And we're done. So we now know that Sylow subgroups exist, but we can say a bit more, and that is the content of the rest of the Sylow theorems. So to say this nicely, let's let, for a finite group G, we can look at the set of Sylow P subgroups, and we'll let in P be the number of them. And the theorem, which has a number of parts, says that if P divides the order of the group, then on the one hand, there are Sylow P subgroups. Okay, so they exist. Part number two, they're conjugate. For all P and Q Sylow P subgroups, there exists some G and G such that GPG inverse is Q. Okay. All these Sylow subgroups are conjugate. In fact, you can do a little bit better. Maybe I'll call this 2.5. Says that if P is a Sylow P subgroup, and if Q is any subgroup whose order is a power of P, P to the L, for some L, then you can conjugate Q to make it sit inside of P for some G. So if you have a Q that isn't necessarily as big as possible, maybe it's not conjugate to a Sylow because it's not big enough, but it's conjugate to something inside of any fixed Sylow subgroup. Okay, 2.5. How about part number 3? Has to do with what properties these numbers have. So on the one hand, the number of P Sylow subgroups has to be congruent to 1 modulo P. And let's say the other part of this, maybe I'll call this 3.5, is that the number of P Sylow subgroups has to divide the index of any of the P Sylow subgroups. So it divides the order of the index in G of P for any P Sylow P subgroup of G. Okay, so there's a lot of parts to this. Part number 1 is what we've already shown, but all these other ones are what we have to do next. That these are all conjugate, and counting them up. And to do this, really it boils down to understanding the action of conjugation on the different Sylow subgroups, both by the group and by the Sylow subgroups themselves. Okay, so let's suppose we have some group, and we consider it Sylow P subgroups, and we have, let's say, Q is some subgroup of G is a P subgroup, is a P group. So in other words, the order of Q is, I don't know, P to the L for some L. Now, of course, G acts on the Sylow P subgroups by conjugation, right? So G, G acting on P by definition is GPG inverse. And this action restricts to an action of Q on the Sylow P subgroups. And let's consider what we can say about the orbits under this action by Q. Okay? So if I look at P, Sylow P subgroup, then I can ask what's the orbit of P under Q. And then how big is that orbit? Well, by definition, we can, we can use the orbit stabilizer theorem to talk about that. So the size of this orbit is the size of Q divided by the size of the stabilizer in Q of the point P, the P thought of as a point in the set that I'm acting on. And the size of the stabilizer is, well, what is the stabilizer? The stabilizer are the elements, I don't know, Q and Q, which when you conjugate QP, Q inverse, give you back P. We have a word for that that's called the normalizer. So in other words, these are things in Q which also normalize P. Now, it turns out that, in fact, this turns out to be equal to just Q intersect P. Okay, so let's see why that is. So in fact, the claim is that the size of the orbit is really the number of things in Q divided by the number of things in Q intersect P. And that's going to be a very useful fact. So why is this true? Well, one direction is clear. It's clear that that P is contained inside the normalizer of P. If you're in P, then you conjugate P and you're staying in P. So this is all contained inside of here. The trick is, why is this contained inside of there? Well, of course, this is certainly contained inside of Q. So because everything in here is in Q, but why is it all inside of P? That's the only non-trivial thing about this to check. Okay. So why is Q intersect the normalizer contained inside of P? Well, here's why. If you look at this thing, and I'll call this thing H for a moment, then I can look at H times P. What you know is that H times P is actually a group. Why? This is a group, is a subgroup, because H normalizes P, right? By definition, H is the intersection, so it's inside the normalizer. And so that means I can reverse the multiplication, reverse these factors, and that means this is a subgroup. Okay, so this is a subgroup. And well, what do I know about it actually? I also know its order, right? So the order of HP, as we've seen previously, is the order of H times the order of P divided by the order of H intersect P. And everything in sight is a power of P, right? Right, because Q is a P group, so this is inside a P group, this is a power of P. So everything on top is a power of P. I divide it by something, I still have a power of P. This is a power of P. Of course, it contains P, which is a P Sylow subgroup by assumption in the beginning. And well, by definition, the fact that it's a P Sylow subgroup means that that is as big a P group as you get as a subgroup of G. That actually says these are equal. Okay, so P equals HP. Well, so you know that H is contained inside of HP is actually equal to P, and so therefore H is contained inside P, and so these two things are equal. And so I now have a nice description of the size of the orbits. So as a first step to the rest of the Sylow theorems, let's pick a p Sylow subgroup and consider what all of its conjugates look like. So here P is some Sylow subgroup, P Sylow subgroup, and let me consider the set of conjugates of P. We'll call that X. I claim, of course, eventually we're going to show that X is all of the P Sylow subgroups, but we're not there yet. The first thing we're going to do, though, is notice that the number of things in X is congruent to 1 mod P. The way to see that is to consider the action of P on X. Okay? I mean, G acts on X by conjugating, and by restricting that action to P, P acts on X. Now, under that action, X is a disjoint union of orbits. X, disjoint union of orbits. Let's just see what the size of these various orbits are. So, what is the size of the orbit of P prime under P by conjugation? Well, we'll use this fact up here, and it tells us that we can calculate this as the index in P of P intersect P prime. Okay, so what do we know? This thing is equal to, well, a couple of possibilities. Either if P equals P prime, then this is just 1. And if it's not, then this is a strictly smaller thing, and therefore this thing, it's, we'll say bigger than 1 otherwise. But if it's bigger than 1, because it's a divisor of the order of P, which is a P group, it's divisible by P. Divisible by P otherwise. Okay? Now, we're a disjoint union of orbits, and so that says that the size of X is the sum of the size of the orbits. One of them is size 1, and the rest are divisible by P. And so that immediately tells us that this claim is true. The number of things in X is congruent to 1 mod P. Okay. All right, so now we're in a good position to prove the second part of the Sylow theorem. So we know that if we consider the number of conjugates of any given Sylow subgroup, that that's 1 more than a multiple of P. So now suppose that Q is a subgroup of G, which is a P subgroup. Order of Q is, P to the L for some L. Then we can again consider the action of Q on X. So Q moves around these Sylow subgroups. It's X again is a disjoint union of orbits under the action of Q. Orbits, and if let's suppose, what if Q is not contained inside of P prime for all the P primes in X? I claim that's impossible. So let's see if Q wasn't contained in any of these. Well, then the orbit of P prime under Q would have size, the index in Q of the intersection of Q and P prime. And what do we know? We know that if Q is not contained in Q prime, this is a non-trivial divisor of Q, of the order of Q. Therefore, it's divisible by P. So that would say that P would divide that. But P can't divide all the sizes of the orbits, because then the size of X would be divisible by P, and we just figured out that it's 1 more than a multiple of P. Therefore, Q has to be contained in some P prime, for some P prime, but what are P primes are the conjugates, so that means that Q actually is in GPG inverse for some Sylow P subgroup. For every Sylow P subgroup, excuse me, because P was arbitrary. So Q is contained in the conjugate of any Sylow P subgroup. Of course, so that's really part 2.5, but But of course, this also says that if you have two Sylow P subgroups, if Q is also a Sylow P subgroup, then what does this say? It says that Q is, these things are subgroups of the same size, so they would have to be equal. Q would be a conjugate of any fixed Sylow P subgroup, and so all the Sylow P subgroups are conjugate. And that's part 2 and 2.5. All right, we're almost done now. We've shown that if you look at the conjugates of any fixed Sylow P subgroup, you get all of the Sylow P subgroups. We knew that the number of these things is congruent to 1 mod P, and so now we have that NP is congruent modulo P to 1. The only thing left to do is the divisibility part of the NP, and so how does that work? Well, now that we know that everything is just in one orbit under conjugation with respect to G, that tells us that the size of the Sylow P subgroup, set of Sylow P subgroups, by the orbit stabilizer theorem, this is the index in G of the stabilizer of any of the CP-less subgroups, which is the normalizer. It's the things which, when you conjugate by that which you conjugate that Sylow P subgroup by, you get the same subgroup again. And what does that say? It says that now if you look at this, the normalizer, of course, contains the contains the Sylow P subgroup itself. So this is so that means that this divides the index in G of P, and so that tells us that that NP divides the index of any of the Sylow P subgroups, and we're done. That's the end of the Sylow theorem. Sylow theorems.